So let me start with, so we have this project. It's called Network Service Mesh. You'll understand why it's called this in a moment. So first, let's start with a short story, though. So we have this character named Sarah, and we actually use this for most of our introductions because it helps provide a really good story towards something that users often want. So Sarah is writing a Kubernetes application that she wants to deploy to the public cloud. So as part of this, she wants the application to be able to access her corporate intranet. So she wants something that looks like this, that from her point of view, she has her Kubernetes interface, she has an L2, L3 connection to her corporate intranet, there's some security in the middle, and she doesn't want to have to care about the rest of the world. Like, she just wants to have this. So, however, she's forced to care about the network interface. How do you land a second interface into the system? She's forced to care about the subnet, who defines it, what happens if it's too small, like how do you redo this in the future? Who defines this particular interface? How do I take the interfaces from the VPN gateway, and how do I take all those routes and then inject them into the pod? Which means you need things like privileges. If you need more replicas because your subnet's too small, then guess what? You're going to tear all this stuff down, put it back up again. Or suppose that the subnet changes because of some policy. Then you might have some corporate intranet set of routes that have changed, and so now you have to do it again. And so suppose that they decide that now you want to have a firewall that has to sit in the middle of this before you get to the VPN gateway pod. So like we're literally using like 1990s concepts for this type of stuff rather than something that looks more cloud native. So let's back up a little bit and now let's like go back to like network service mesh or to service meshes itself, and then you'll see like how we're approaching this problem and how we're solving for this. So if you think about it, you have service mesh. Most people think of like a application style service mesh, L4, L7. We're aiming for L2, L3. So L2 Ethernet, MPLS, L3 payloads like IP and so on. So if you look at service mesh like Istio or Envoy or so on, you see something that looks like this. So if you notice the Kubernetes interface here is present here, and your Envoy uses it. So what we're doing is we're having something that can go a bit further. So you still have your Kubernetes stuff, and you have this additional set of connectivity that does something interesting for you. So what we're trying to build is something that looks more like this. So you have a client, and this client connects to a network service. And this network service is a chain of various services. It's a graph of various services that you want attached in. There might be a load balancer in here. There might be a firewall. There might be multiple gateways or so on. You don't want to have to care about all that stuff. You just want, the operator can set it up. You as a user should just be able to use it. And so one really good example when we start to look at that is like your Kubernetes networking itself is a network service. So if you think about it, like we want to be able to interpose things. Like we have the network service to your to another network service. So you have something like maybe it goes to a network policy, maybe it goes to Kubernetes services, and you might even stick Envoy in the middle of this, stick it before, then have your thing to actually get to your reachability. And so rather than having like a big black box, like we want to be able to drive this so you can actually start to segment these out, be able to drive so maybe you get the interfaces can be negotiated between different versions. So you have like service A and network policy to your network policy. Maybe that initial one's a kernel interface, but then you do shared memory from the rest because those pods have been designed to do shared memory. So you can get like a lot faster in your data access. So what we want to be able to do, one area that we're looking at is like, okay, well, how do we take this particular pattern and then let's stick like procs, like maybe we stick like Envoy in the middle of that, and that way we can then drive traffic through various types of services. We could have the intelligence of Envoy and be able to also leverage that within the L2 and L3 space as well. So things that we're able to help provide Envoy as well is like perhaps you have a pod that says, I want something that's Envoy, that needs Envoy. And so we could auto-create that Envoy for you, wire you L2 to L3 to it. Perhaps that you want to upgrade to a new version, then you can upgrade, auto-heal those particular connections, make the old one go away, and you're connected. So So that's like the high level view. It's like what we're trying to accomplish with this project. So what is a network service mesh? So when we say network service mesh, we don't typically mean network service mesh. We usually mean a mesh of network services. So that's one key difference that we have. So from a developer's perspective, you care about things like the treatment of packets that you have. You care about connectivity, security, you care about some service being provided to you, proxying, load balancing, network address translation, or so on. But you want something that's in the middle of this, but you want to have to not care about it either. So as a developer, you want to name the thing that you want, be able to add metadata to the thing that you want, but you don't want to have to be able to say, like, how many of you know what an MPLS label is? If you worked in telco, you know what it is, or if you worked in some of the service providers, you know what it is. Like, you don't want to have to deal with these type of things. And so, but they're necessary for certain types of telcos and operations to work. So, so going back to Sarah's example, so we have the security goes here. So like that's the thing that the developer wants. They want something that looks more like this, not something that looks more like the initial version of what we showed. So let's go ahead and take a look at what network service is. So we have a client, we have an endpoint, and then the third concept is we have the L2, L3 connection. So those are our three primitives. And as you can see, client, endpoint, and each of these purple ones is the connection. So these particular endpoints, they don't have to be pods. So we've also designed the protocol in such a way. So we use gRPC for our protocol translation, and so we actually can connect you to other things besides pods, so VMs, physical network functions, physical devices, or so on. But as a user, you don't want to have to know about any of that. You just want to say, connect me to something, you get it. And so in this particular scenario, you can also set up multiple connections. So maybe this one connects you to some internet, corporate internet. Maybe this one here gets you access to some network slice somewhere and you're doing something over a radio. Maybe some Internet of Things related thing. So we also have the ability to accept multiple connections coming in. So that way you can do muxing and demuxing. The ability to set up multiple paths, that way you can have additional redundancy. And so how does this actually work then? So at the very beginning, I mentioned we have gRPC. We start off with a request, and that request gets mapped to an endpoint. Some connection gets created. And then there's also a close that works in the same way. So with more detail, you have a request. The request is asking for a specific use case, a specific application, and a specific version. And so that gets mapped to something that has those labels and is capable of consuming those labels to provide you with the thing that you want. Or in more detail, you could also include information like, please do not collide with these prefixes because they're important to me. Like my Kubernetes runs on 10.10 and my internet runs on 5.5.0.0. So please do not interfere with these. These get passed in. That's part of a connection context. Then we perform the connection. So typically the workflow looks more like this. You make the initial request, and this request includes information about its capabilities. So the capabilities could be like, I support kernel interface, or I support memory interfaces. So if you want to get really fast, you can do shared memory from pod to pod as a connection. So you listen to request some information about your capabilities and what you want to connect to. Then, so that gets forwarded to whatever service. This is assuming that's on a single node to start off with. So that gets forwarded off to your service, who then receives that request, makes a decision, do I accept or do I reject it? And let's assume that it accepts it. So we create the right side of the tunnel. That actually gets you the connectivity to the thing that you want. You have the data plane that you're connected to. We create the left side of the tunnel. We program the data plane with a cross connect to create that tunnel. And then we'll respond and say, you're good to go. So this pattern works regardless as to what you're working with, whether you're trying to do some type of VPN, whether you're trying to do some fast access to some data plane somewhere, whether you're trying to do like VXLAN or some other esoteric protocol. So from a multi-node, same pattern, except in this scenario, we ask Kubernetes API server for where the network service endpoint lives. So it responds back with, okay, well, this lives on node 2. So we forward the request. Now, a key difference here is that this forwarding request will include information about the capabilities of Node 1's data plane. So Node 1's data plane might say, I support VXLAN or GRE or some special tunneling for encapsulating the packets. And these are my preferred parameters. And that gets sent off with the request. So the request gets sent off, accepted. This part looks exactly like it did before. The interface gets created. But we build the right side of the tunnel in this scenario, and that right side of the tunnel, it might say, I selected VXLAN as my encapsulation. And so it'll respond back with the parameters that was used in order to connect to it. And that allows you to create the left side of the interface and program the left side of the tunnel, so now you have a full end-to-end tunnel. So we can create these tunnels across a variety of different data planes, variety of different types of tunnels, as long as the API has been implemented. And then, of course, we respond back saying, hey, you're good to go. So we also do the composition as well. So composition was how you actually get multiple endpoints working with each other. So in this scenario, we have an endpoint with an app equal firewall, and we have this one, the app equal VPN gateway. And so what we do is when it connects, this is also a client. In addition to being an endpoint, it's also a client. So it says, I'm a firewall, I'm connecting to secure internet connectivity. And then that'll say, oh, well, I need to connect you to the VPN gateway pod. So you can see on here, the source selector is app firewall. The destination here is VPN gateway. And the name of it is secure internet connectivity. So with those three things, when an app firewall labeled system tries to connect in, it'll get connected directly to the VPN gateway pod. We do the same thing on Sarah's pod as well. So Sarah, the source selector does not match the firewall. So instead, we're able to match the default selector is you connect to the firewall. So with that, we're able to perform that particular connection. So you can make arbitrary types of connections, very similar to like Istio. So we borrowed some concepts from Istio in order to do that L2, L3 matching. And so why is this particular thing important? So with this type of system, we're able to inject interfaces of multiple types that are not kernel interfaces. If you want to saturate 100 gig NIC cards, this is a very good path to do it. You could potentially have something like Nginx doing something like shared memory to your data plane. Your data plane then does direct memory access to your NIC card, and so the performance of this is literally how fast can you write to memory? How fast is your PCI Express bus, your motherboard? How fast is your NIC card? And so with these particular patterns, we're able to do like full kernel bypass and land you to the things that you want. We're also able to, as we mentioned before in the Kubernetes service, like suppose we were to do something like Kubernetes networking. We could do the ingress controller, the egress controller, do the service mapping and so on, wire envoy in, be able to do shared memory between each one of these. And you've also now have it disaggregated so that you can actually run each one of these as pods, which gives you additional insight, like how many resources, like how many CPU cycles, how much memory is my ingress taking, my egress, what about my services? What happens when one of these crashes? It's like, right, the error recovery is not simple. So we'd be able to take this to a much more simple approach and get something that's a lot more flexible. You'd be able to say, I want to be able to inject a firewall into this system based upon my corporate security policy. So how do you inject firewalls in? And so there's a lot of flexibility that we can help drive in through this. And with that, if anyone is interested in getting involved, we have networkservicemesh.io. We have a GitHub page. Everything is open source. We have our general meetings on Tuesday, and we are looking for help to help complete some of the Envoy use cases. So I know that I've spoken to a couple of people who are willing to help out. But if you're interested in trying to work out how do we bridge L4 and 7 and drive L2 and L3 connections in addition to that, like definitely please come and talk with me. And with that, are there any questions or?
We have time for questions. A couple.
Sure.
Does this use the Kubernetes control plane to send down all the YAMLs and the configuration and how you do the forwarding?
Okay, so the question is, are we using Kubernetes control plane? So the only thing we're using Kubernetes control plane in this scenario is for the storing of the where things are within the Kubernetes system. So where do the endpoints live? So everything else is the control plane is all gRPC. And so it's a distributed system. So this is most SDNs are, we're not an SDN. We're a matchmaker and we help control. You can think of it like controller of controllers. So we will derive you information so that based upon the context using gRPC, and so that way you can then make the decision. But this was designed to complement Kubernetes but not require it, because some of our use cases we're looking at are, how do you bring an OpenStack? How do you bring in things like physical networks, physical devices where Kubernetes may not be there? So in fact, our Kubernetes APIs that we hit for the registry are actually fronted by a gRPC service, and so you could actually stick some other database behind it as well. We just found that having Kubernetes, though, it makes it very convenient.
Does your solution predominantly use an overlay, or does it not use an overlay?
Okay, so more clearly, we are not the overlay itself. We drive you to the overlay. So we will help establish connections which may or may not be an overlay. So it depends on how you decide to compose it. So if you want an overlay to be there, and you set up your data planes in that way to have an overlay, you'll have an overlay. If you want to have something that does not use overlay, it's all bare metal all the way down to getting you to a physical device, and that device is something that is very physical and tangible, then you can drive that use case as well. So our job in Network Service Mesh is not to be that connection for you. We don't sit in the middle of it. We just pair things together, like the client with something that provides you the service you're asking for.
So does it work like a calico then, where you modify the IP tables so that you can establish do you have a gRPC API manager that brings these connections on the side?
Okay, so what we end up doing is we have a gRPC-based API that the data planes are able to implement, and then we say, this is the type of connection we want to make, and then the data plane will go and build those connections. So we don't manipulate IP tables ourselves, but the thing that you're working with could manipulate IP tables if it chose to do so. So, but we don't have, Network Service Mesh itself does not sit in the middle. So, because if you sit in the middle, you're something that may slow down the connection or add complexity to it. So, we pair you up with the data plane and pair you up with the remote data plane, we pair you up with that thing that you want to connect to, and then get out of the way once we've helped negotiate that connection. Sure.
How does this work with the existing CNI plugins?
Okay, so right now we are complementary to the CNI plugin, so we make an effort to not interfere with them. And so your mileage may vary to some degree, because that's what part of the reason we have the information on there is like which prefixes do you not want to modify, because we don't want to affect Kubernetes networking. So, and if you're going with shared memory, then you're in full control, because you're doing packet generation in user space, and then you're driving that user space connectivity. For users who really care about that matters a lot, because the kernel interfaces will get you maybe around 1% of the total performance of what like a shared memory-based system will get you. So like if you were to implement like Nginx or some other similar thing, and you want to like maximize that throughput, like this would be a very important use case for that. And so, are we good? Okay, we're out of time. Cool. So thank you very much.
Thanks.